Hello, this is Dr. Jason Harrington, and today we're going to talk about what is a differential equation. So an equation consisting of derivatives of one or more unknown functions with respect to one or more variables. That's what a differential equation is. So let's just go over some examples. Now you'll notice, or recall, this is from calculus. You've actually dealt with differential equations before. So you've seen things like dy over dx. That's a derivative with respect to y, and we'll say that's just equal to x. Now we learned from calculus that the answer for this is going to be y is equal to 1/2 x squared, and you can't forget that little constant out to the side. So here we have a differential equation. And over here we have our solution. And basically in this class we're going to learn how to find more complex solutions to differential equations, or more solutions. Another example we can see is if we have something like the derivative of y with respect to x plus 2 is equal to the second derivative of y with respect to x. That's also a differential equation. All right. And another example I can do, maybe something that you've seen from Calc 3, is you can have maybe the partial derivative of z with respect to the partial derivative of x plus the partial derivative of z with respect to the partial derivative of y is, say, equal to x plus y. So again, that's another dE. And the purpose of this class is that we're going to be figuring out how to construct these differential equations and then how to solve them. Before we do that, we have to learn a little bit of lingo about how to describe and classify. Okay. So there are two main types of differential equations. The first one is going to be the one we're going to be dealing with primarily. So the first type we're going to call ordinary differential equations. Ordinary differential equations. And these are when you take the derivative with respect to just one variable, not two. So for this, we're going to be, again, you want to take the derivative with respect to just one variable. And that's what this class is actually all about. So an example of this would be if I take the derivative of y with respect to x, and I'll write, again, that example that we did from Calc 1, and just say x. Another example, we can also do things like take the second derivative of y with respect to x, and we can also take the first derivative of y with respect to x and say equal to 0. So the thing that you want to notice here is that we're always taking the derivative with respect to one variable. The second one that we have, and by the way, in this course, we'll typically refer to these as ODEs, ordinary differential equations. The second one is what's called partial differential equations. And for that, we'll actually abbreviate that PDE. Whoops, PDE. Whoops, PDE. All right. An example of that would be when you take the derivative with respect to two or more. So for this, it's going to be with respect to two or more for its derivative. So for example, if I have something like the partial of z with respect to x plus the partial of z with respect to y is equal to 2. Or you can have something like many different types of taking the derivative with respect to, say, 2 or more variables. You can have the partial of w with respect to x plus the partial of w with respect to y plus 4 times the partial derivative of w with respect to z is equal to 1. And those are examples of partial differential equations. Now, this class is going to primarily focus on the first one, and there will be other classes that you'll take later on that mention partial differential equations. But we're primarily going to be focusing on how to solve and solve differential equations when you take the derivative with respect to just one variable. The order of a differential equation is the order of the highest order derivative present in the equation. So let's do some examples really quickly. So if I have a differential equation that's, say, going to be dy over dx plus the second derivative of y with respect to dx plus e to the x equals sine of x, for example. We see that we look at each term. So this term is order 1. This term is order 2. And these two terms here are both order 0, because there's no derivatives there. So that means that we're going to take the highest. So we have order 1, order 2, and order 0. So the highest order is 2. So the order of the ODE is 2. Now the next example I want to give, if I look at something like the square root of 1 plus the third derivative of y with respect to x plus sine of x times the derivative of y with respect to x is equal to 2, or just put 2, what we can see is we look at each order. In this case, this is order 3. This little guy is order 1. So the order of this ODE is the highest, which is 3. Is 3. Now I do want to state a word of caution, which we'll talk about a little bit more, but this next example, I'm going to have the first derivative of y with respect to x squared plus 4x minus 1 is equal to e to the x. Again, this guy right here, this is just order 1. Remember, this is saying take the partial derivative, or take the derivative of y with respect to x and just multiply it with itself twice. But you're only taking one derivative. So sometimes people tend to miss that. So here, the order of the ODE is 1. So basically, you're just looking for the highest derivative that you'll be taking, or the derivative of the highest order. Now, please note, you want to be very careful with notation. So let's recall, and again, this is from Calc 1. If we have a function, let's say, let's let y is equal to a function f of x, then we will say the derivative of y with respect to x is the same thing as saying the derivative of y with respect to x, which is also the same thing as simply saying y prime, or even just writing f prime of x. Now, all these different notations will be used, but let me just make sure you understand how all this works. In the first one, we see that this is basically one token that says take the derivative with respect to x. So when you take the second derivative, that means you're going to have d over dx times, or take the derivative, not times, but take the derivative of y with respect to x, and then take the derivative yet again. And when you combine this notation, you'll notice that the d over dx, that's again like one token to indicate we're taking the derivative with respect to x. That's going to turn into d squared y over dx squared. When I was an undergrad, I used to always think, why isn't the bottom d squared? But it's really, this is just one unit. This is like with respect to x is what this says. Now, this is not the same, right? You don't want to write this is a big no. You do not want to write this as the same as dy over dx squared, because this is the same as saying take the derivative of y with respect to x and multiply that by taking the derivative of y with respect to x again. So again, this is the second derivative, and this is just the first derivative twice. And so you want to make sure to avoid that. And also note, we also have some other notation. So when we write dy over dx, this is called Leibniz notation. Which this is also the same as saying y prime, and that we just call prime notation. If we write it like y dot, that's typically given as Newton's notation. And if we go into higher and higher dimensions, we can see that we can have other notation as well. So here's another example. Suppose I have, again, I'm going to have y is equal to f of x, just like before. But now I'm going to look at the second derivative. So I'll have the second derivative of y with respect to x. That's, again, Leibniz notation. And again, I can write y double prime in my prime notation. And I can also write this as y two dots in Newton's notation. I'll just call that Newton. And sometimes you'll even see it written as y of xx, kind of like what you saw in the Calc 3 class when you see the subscripts indicate taking the derivative. And we just call this the subscript notation. So you can see there's different ways to write them, to write taking just even the second derivative. But they're all interchangeable, and so you'll want to get used to writing out the derivative in different ways, so that way it doesn't confuse you on a test or confuse you with the homework. All right, so our next definition is, what does it mean to be linear? And that's actually a little typo up there, just the nth order. The text part shouldn't say that. So an nth order ODE is linear if it's of that particular form. Now what you'll notice is that you're going to have derivatives and you're going to have functions in front of the derivatives, and that's okay. And that means it's linear. So for example, if I say something like e to the x times the second derivative of y with respect to x plus sine of x times the first derivative over dx, and this is going to be equal to another function, let's just say the natural log of x. Now what you'll notice is that each one of these, it's a function times the derivative, and we also have a function times the derivative, and that's what we mean to be linear. Something that's not linear, so I'll put this over here, this is in fact linear. Things that are not linear, for example, was like that example that I gave earlier with the square roots. If I had, say, the square root of 1 plus the derivative of y with respect to x plus the third derivative of y with respect to x cubed minus the natural log of x times the first derivative of y with respect to x, and say that's equal to 0. Now, if you look at this, these two terms are actually linear, right? You have a derivative, and then you have a function in front of that derivative. You have the third derivative, and in front of this you have a 1. That's perfectly okay. But this is the term that makes it nonlinear. Because now I'm not just having the square root by itself, or I'm not having the derivative by itself. I'm taking the square root with the derivative inside. So this is not linear. Another example that's linear is if I give a function like x times the derivative of y with respect to x minus y times the second derivative of y with respect to x plus the third derivative of y with respect to x equal to 0. That is in fact linear. So as long as you just have a function and then you have the second, third, or nth derivative, and on each piece, then that's good and linear. Like this term here, I had a function times dy over dx, a function times the second derivative, and again, if there's nothing there, then you'll have that 1 there as your function in front of the third derivative. So things that are not linear, typically you'll have the derivative inside of something else. Or you'll have the derivative mixed in with other functions, inside of functions. But if the functions are outside of all of the derivatives, then we call that linear. So when you look at an ODE, for example, we'll have dy over dx is equal to x squared plus y. The question is, which one is the independent variable and which one is the dependent variable? Well, Basically, this, when you take something with respect to a variable, those are typically independent. And the function that you're taking the derivative with respect to is dependent. Because that function depends on x. It's a function in terms of x. So, i.e., y is a function in terms of x. When we actually solve these things, you'll see that if you were to solve this, what would the solution look like? What you're looking for is the function y of x. So the solution is going to look something like y of x equals ... whatever that may be. So let's do an example from that Calc 2 example that we did before. If I say the derivative of y with respect to x is equal to x, we know from Calc 1, one of those calculus classes, you're going to see the answer is y of x is equal to 1/2 x squared plus c. And just like the definitions of like domain and range and input versus output, what you see is this is going to be a function in terms of y. So just by looking at the ODE, we can see that this is going to be dependent, dent, dependent, put a little t there by accident, and this little guy is going to be independent. Now these, of course, are very two simple examples. So let's try to look at one a little bit more complicated. If I were to say, let's take the second partial of w with respect to x plus, let's do 5e to the x plus y times the second partial of w with respect to y is equal to 0. Again, just by looking at this, you're going to see that the dependent variable is w. Whoops. And so that's our dependent. And our independent whoops, I did it again. Independent variable. And we're going to actually have two of these. We're going to have y, and we're going to have x. So we're going to have x, comma, y. And we know that the solution for this is going to look like something of w in terms of x and y is going to look like of that form. So we have a multivariate function of x and y. Probably the most difficult part about this particular section that I've encountered is spelling independent. All right, let's try another example. This one says classify the difference equation by its type, order, and linearity yet again. So the first thing I'm going to notice is that each one of these has the term, or you're taking the derivative with respect to x. So basically, because I'm only taking the derivative with respect to x only, we see this is yet another ODE, ordinary differential equation. The second thing is, so again, that's what we say by type. The second thing is, what is the order of it? So again, you're going to look at each piece and see what is the highest order derivative. Now in this case, you see that we have the third derivative plus the first derivative, or the square root of 1 plus the third derivative. And that's the highest order. So the highest order is 3, so we're going to have the order is 3. And the third thing is it in fact linear? Now remember, linear means it's just going to have a function times a derivative of some order. In this case, because I have the square root of 1 plus the third derivative of y with respect to x, right here, that's inside the square root. So that means this is not linear. We want to clarify the differential equation by type, order, and linearity yet again. So let's go ahead and get started. The first one says, what is the type? Now you'll notice in this case that we're taking the derivative with respect to x and y. So we take the derivative with respect to x and y, so that means this is going to be a partial differential equation. The second thing is well, what about the order? So you see in the first term, we're taking the partial derivative of w with respect to x. So that's order 2. The second one is the partial derivative of z with respect to y, and that's just order 1. And then on the other side of the equals, we don't have any derivatives. So that order is 0. So the highest is order 2. So we have that this is going to be order 2. And again, you can also say second order. And the third thing is this linear? Now you'll notice with each one of these terms, so here I have the second derivative of w with respect to x times a function, x. And then I have the partial derivative of of z with respect to y, and I have a function in front of that. So that is in fact linear. And so anytime you start working on a differential equation, the first thing you want to do is you want to be able to identify it right away, because usually that will help you figure out what tools and techniques you have to solve it. Hopefully all this makes sense.